Worksheet 9A, shear and moment diagram. Calculate the support reaction and draw the shear and bending moment diagrams for the beam loaded as shown. And this is simple supported beam, pins at A and roller at B. So from this one, as you can see, the reaction, it will be the same at A and B because it's symmetrical. For the distributed load, 200 Newton meter for 6 meters, so it will be 120. You may use the 3 equilibrium equation to find out, but otherwise, you can see that reaction at A and B both vertical, and it will be 60 Newton going up. 60 Newton, half of the 20 Newton meter times 6, 120 Newton. So always start with shear, and that we already talking about. Start with from left and start at 0. And at A we have 60 Newton up, so it will be cause the discontinuity move up, move up there, 60. And then between A to for 4 meter to the left before the distributed load, there nothing, so the shear remain unchanged, horizontal 60. And then now the change between this point 4 meter from left to 10 meter from left, which is the 6 feet under the uniform distributed load 20 Newton per meter. And you can see that areas here is negative 120 Newton for the area under the distributed load. 120 negative, that equal to the change in shear diagram, and in this case negative, so it will be N go down. The uniform distributed load, it causes a continual change in the shear diagram. So negative 120 from positive 60, it going down to here, and you can see that is the negative 60 to make that equal to negative 120, the change from in this 6 meter. So it's 0 in the middle, change go down to negative 60. And then from out of the distributed load, the remaining 4 meter nothing, so you will have same shear throughout, negative 60. And then they are distributed the concentrated load, in this case the external load applied on B 60 Newton up, so it will be move up, discontinuity in the shear 60 Newton move up, so that it will be 0. So start at 0 and finish at 0. That's what you have for the shear diagram. And we can go ahead to write out, this is straight line, this is straight line, and this is straight line. So no distributed load, then the shear will be horizontal, same shear throughout at the first 4 meter and the last 4 meter of the beam. In the middle 6 meter, and you can see 20 Newton meter horizontal, 20 Newton meter uniform distributed load, then the shear will be have the change, continuous change in the slope of the shear diagram. Continuous change, so it will be straight line. So now moment, before we find out the area under the shear curve. So let's break down here, The first area 16 times 4, so you have plus 240. This 4 meter on the right, similarly negative 240. And 60, the first triangle here, and you can see, and it because it's symmetrical, so you have that is 3 meter and 3 meter here. So instead of the triangle, you have 16 times 3, divided by 2. So 60 times 3 equal to 180 divided by 2 because that triangles. So it will be plus 90 in there for that area. 90 to 40. And that one, it will be negative 90, negative 60 times 3 divided by 2. So triangles, keep that in mind, not 180. You have to divide by 2. So go to the moment diagram. When moment diagram, look at the shear diagram. The change in moment equal to the area under the shear curve. So 250 for the first 4 meter. So always start at 0, 240, so 200, 300, so 350. So 240 here. And the shear is constant, so slope it will be straight line in the moment. So it will be S in here. And now 90, and in the middle 6 meter, as you can see, uniform distributed load, the slope of the shear equal to the magnitude of the distributed load, that is 20 Newton meter, and the slope of the shear of the moment diagram equal to the magnitude of the shear. The shear changing, and you can see between here, change from there 60 to here 0. So the slope change. So with that, it distributed load is uniform. Then it becomes a parabola for the moment. So 240 change plus 90. So 240 plus 90 equal in the middle is 335. 330. Sorry, 330. So it's in the middle. That make down here. Now, so 330 so here plus 330 Newton meter. 330 Newton meter. And as you can see, for the shear from here plus 60, go in the middle is 0. Middle is 0. So it will be, by now you know the curve of the parabola, it will be curve up here, so that it will be have slope at 0 in the middle. Why that it not the other way? Go back to the example that we showed in example 2 and example 4 in the lesson note. And now for the second half, you can have negative 90, so of course it's symmetrical. It have to be, and the shear start from 0 in the middle, go down here, it negative 60. So the slope, let's change the color, blue here, go down, and then negative 240 and no distributed load. So the shear the same. So as you can see, slope here equal to the shear throughout 60, negative 60. So it will be going down for 60, and from 240 here going down to that, it equal to 0. So that stop at 0 in there. So you can see that point here plus 240, 330 plus 90, now plus negative 90. So you have is plus 240 at that point, and then 0 in there. So what do we have? Straight line in the last 4 meter, and of course this is parabola. Makes sense? And it's 0 in the middle. That's why the curve here, you can see tangential, it will be horizontal in that point, and which it makes sense from this diagram. As you can see, this diagram makes sense because with that it all is positive moment, because it creates the throughout the beam it bending that have a tension in the bottom and compression in the top, and the maximum moment in this beam is 330 30 Newton meter, and the maximum shear is internal shear is 60 Newton.